right, guys. So for those who missed class today, we went over the answers to these questions, and I just want to go through them with you guys. Um, and so here, let's start with number 36 here, and we have an RC circuit in series, connected in series to a battery with terminal voltage V0, and it asks which of the following equations relates the current and the charge. Well, I mean, connected in series, so I think you should have in your mind this idea. We've got the battery and our resistor here, and connected in series with a capacitor. And so this is an RC circuit, kind of classic RC circuit. And the drawing's not so great because I have to draw with my touchpad, but it's not too bad. All right, so we have our RC circuit, and you think, okay, how do we figure out what the voltage is across these elements? And you're just taking a Kirchhoff's loop, essentially, right? And I'm not expecting, you guys should not be drawing this in the test. You should just have it down, but think about it quickly, and if you put it together like this, you have that vision in your mind, it should be pretty clear what the answer is, because if you take that Kirchhoff's loop, you go around the circuit, and you've got the voltage V minus IR, direction of the current is, take the loop in the direction of the current, minus, well, what's the voltage across the capacitor? Well, Q equals CV, so Q over C is the voltage. And that whole thing, if you add it up, Kirchhoff's loop rule says that equals 0. So you should see, obviously, okay, answer is B. And if it's, if it doesn't come to mind right away, again, then you should draw that circuit, have that, take that Kirchhoff's loop, and that's what we've done for our RC circuits in general. Okay, well, let's go ahead and look at number 37 here. And so we have our combination of 4 ohm resistors, and which of these combinations would dissipate 24 watts when connected to a 12-volt battery? Well, we have to think right away. And teachers, we say, oh, don't memorize the formulas. We don't have to memorize the formulas. They are given on the sheet. But if you do memorize it, guess what? That's just going to save you a whole lot of time, not having to keep referring back to the equation sheet. And so you might just know my whole thing with power is VIP, right? VI equals P, or P equals VI, right? So if you have that down, okay, voltage times current equals power, and how do I relate that to resistance? Well, that would be V equals IR, so replace I here with V over R, so you'd get V squared over R. V squared over R equals P, and so having that idea in mind, we have V squared divided by R is our power. And so now we want to know, well, voltage is 12, so 12 squared, 144. 144 divided by what value of R would give us 24? Well, obviously, you do the calculation, you find out that, of course, 144 divided by 24, divided by 24 equals 6, right? And that would give you, well, I need an equivalent resistance of 6. So what combination of 4 would give me 6? Well, obviously not A, that's 8. Any of these in series, those two are out. And so let's come over here, and what do I have here? I have 8 in combination parallel with a 4. So 1 over 8 plus 1 over 4 would be 0.375. Well, that can't be right. That's 3/8. That's 8 over 3. That doesn't work. And so you come over here, and you logically you'll get the right answer here. You get the right answer. It's not obviously not B. That's going to be too small. E is the correct answer. You've got 4, 4, 1 over each makes 2. 4 in parallel. Sorry, 4 in series with 2 makes 6. So you get the answer E. So we're at first one's B, second one's 36 is B, 37 is E. All right, let's come down to 38 here. 38, we have 2 initially uncharged conductors, 1 and 2, are mounted on insulating stands and are in contact as shown above. A negatively charged rod is brought near but does not touch them. With the rod in place, conductor 2 is moved to the right by pushing its stand so that the conductors are separated. Which of the following is now true of conductor 2? So the rod is brought near, and these two are in contact. So what's going to happen is, of course, this is going to get polarized. Positive charges are going to come over here to sphere number 1, and negatives are going to go as far away as they can to get away from that negative rod. So they're going to come over to ball number 2. It's important that it notes that you pull the stands apart before moving the rod while the rod is held in place. Why is that important? So that these things stay polarized. And when you separate, now there's a net charge negative on ball number 2 and net positive on ball number 1. Okay, so with that, the answer is C. It is negatively charged. Ball number 2 is negatively charged. All right, let's come forward and look at 39 and see what we can do. Okay, so far not too bad. Of the 2 circuit ones, we did have used a few formulas. That last question just completely conceptual. Let's take a look at 39 and 40. As shown above, 2 particles, each of charge positive big Q, are fixed at opposite corners of a square that lies in the plane of the page. A positive test charge, positive little q, is placed at a third corner. What is the direction of the force on the test charge due to the other 2 charges? Well, obviously, it's repulsion, and so you're going to get something down and to the left. And so the answer obviously has to be E as a vector sum. And for 4, if F is the magnitude of the force of the test charges due to one of the other charges, what is the magnitude of the net force on the test charge due to both? Well, 45-degree angle. You've got F pushing away. Let's make sure we see that. Okay, right? So why is it E? We've got F pushing away from the top one here, F pushing away from the one on the right. And so what is that? That's a hypotenuse. Everything's equal here, and this will make a 45-degree angle because we have an isosceles triangle effectively. And so root 2, if one of these is F, combined together, we get root 2, right? F and F. But I don't need to do it, right? F root 2F. So D is the correct answer. Okay. All right. Hopefully that one wasn't too bad. 41. Gauss's law provides a convenient way to calculate the electric field outside and near each of the following isolated charge conductors, except A. So here we have a Gauss's law problem, and of course that's our heavily abstract one conceptually. So let's see. Gauss's law provides a convenient way to calculate the electric field outside and near each of the following isolated charge conductors, except A, a large plate, sphere, cube, long solid rod, long hollow cylinder. Remember, we use it when there's a convenient symmetry, and we've done the large plate, so we did that. Of course, we've done a sphere. That's one of the most common ones, spherically symmetric. Have we done a cube? No, we have not. C is the answer because we've done a long solid rod. That's just a cylinder. And of course, a long hollow cylinder is also the same thing. So, of course, C is the answer. We've never done a cube using Gauss's law. And it does not have the symmetry that makes it easy to do. Remember, there's spherical symmetry, there's coaxial or cylindrical symmetry, and then there's planar symmetry. And those are the 3 symmetries that we can use Gauss's law for. All right, 42. A wire of resistance R dissipates power when a current I passes through it. The wire is replaced by another wire with a resistance 3R. The power dissipated by the new wire with the same current is, and again, VIP. This is VIP, and so if you have that in your mind, you've got that memorized. How do we get this in terms of R again? Now we want it in terms of R and current. So V is IR, so this is just going to be I squared R. So now we've tripled resistance, and how will power change if it's the same current? We've tripled resistance. I squared R says we're going to triple power. It's D. Okay. So, all right, coming back here. Questions 43 and 44. A narrow beam of protons produces a current of 1.6 times 10 to the minus 3 amps. There are 10 to the 9 protons in each meter along the beam. Oh, great. So we got some calculations with the electric charge. Of the following, what is the best estimate of the average speed of the protons in the beam? So we have a current 1.6 times 10 to the minus 3 amps. How do we relate that to Q? That is Q over time, right? So that's Q over time. So Q coulombs over seconds is amps. And we have 10 to the 9 protons in each meter. So how many protons how much charge do we have in each meter? Well, if I've got 10 to the 9 protons in each meter, what's the charge of a proton? Charge of a proton is same as charge of an electron, 1.6 times 10 to the negative 19. Oops, sorry, excuse me, 1.6. I needed to write that. What have I done here? Oh no, this thing. There you go, 10 to the 9, and we're going to multiply by basically 10 to the negative 19. All right, with a number 1.6, but it's just going to be power of 10. If we get the power of 10 correct, we're going to get the right answer, so don't worry about the factor here. So that makes, we multiply that, that makes 10 to the negative 10, 10 to the negative 10 coulombs in every meter, right? And it says we have a current of 1.6 times 10 to the negative 3 amps. So to get the speed, we're going to take 10 to the negative 10 coulombs per meter. And how do we get the speed? Well, if this is, make sure I have this right. Let's see if this is coulombs per meter. Then I've got 1.6 10 to the negative 3 coulombs per second. How do I get meters per second? I'm going to take 10 to the negative 3 and divide it by 10 to the negative 10. Coulombs are going to cancel, and I'll get meters per second. I'll get the speed. So that will be 10 to the negative 3 divided by 10 to the negative 10, 10 to the positive 7. The answer must be D. All right, just so we check that again. How did we get that? How did we come up with that? We have 10 to the 9. Just give our answer again. 10 to the 9 protons per meter. I multiply by the charge of an electron to get coulombs per meter, right? 10 to the negative 19 is the number of coulombs in a proton. And notice protons are going to cancel out there, so you're going to have coulombs per meter. So 10 to the negative 10 coulombs per meter, and the current is 1.6 times 10 to the minus 3 coulombs per second. To get meters per second, we're just going to divide. It's really essentially comes down to a unit analysis problem, and I'm going to talk about that in a minute. We've got questions that are just based on units that we can figure out just based on units. Okay, so 44. Which of the following describes the lines of magnetic field in the vicinity of the beam due to the beam's current? So I've got positive charge moving along the beam. Which of the following describes the lines of magnetic field in the vicinity of the beam due to the beam's current? Concentric circles around the beam, parallel to the beam, radial and toward the beam, radial and away from the beam. There is no magnetic field. I've got a current of positive charge moving in a beam. That's just a current in a wire. That's the same thing. That's the exact same thing as a current in a wire. Positive charge is moving in the direction of the wire. Well, what kind of magnetic field does a wire create? Of course, it creates concentric circles around the beam. Okay, so don't be confused by the proton and it moving in a beam. They're using some trick words to try to confuse us and make us think that it's some kind of Star Trek thing going on here, and it's not. It's positive charges moving. We know what positive charges moving in a straight line look like. Positive charge moving in a straight line is a current in a wire. All right, so they're just playing with words, and we have to be ready for it. And that's one of the way these AP guys try to trick us. They use vocabulary that we're not used to, we had that question where there was a cat involved. Oh, great! What does a cat have to do with physics? A fly. They have these ridiculous questions. All right, but don't let it fluster us. Don't let it fluster you guys. Questions 45 and 46 refer to two charges located on the line shown in the figure below, in which the charge at point I is positive 3q and the charge at point 3 is 2q. Point 2 is halfway between the points 1 and 3. Okay, two charges on the line, different magnitude, but same sign. Other than at infinity, the electric field strength is 0 at a point on the line at which of the following ranges? To the left of 1, between 1 and 2, between 2 and 3, to the right of 3, none. Okay, well, where is the electric field going to balance out? Think of what these positive charges are doing. The 3 is pushing away everything around it, right? And the 2 is pushing away everything around it. Where is that going to cancel out? Where are those electric field lines going to cancel each other out? Obviously, it's got to be somewhere between 1 and 3 along this line where you have these arrows in conflict. How come it can't be over here? Because both of them are going to be pushing stuff away out there. And it can't be over here for the same reason. Both of them are pushing stuff away along this line. So it has to be in between. Now it comes down to the magnitudes. The 3Q is bigger than the 2Q. So anything over here, 3Q is going to win. It's got to be somewhere in between 2 and 3, right? It has to be here in region C. The electric field goes as Q over R squared, and it's got to depend on R inversely, so it's got to be over here. Okay, so 46. The electric potential is negative at some points on the line in which of the following ranges? Ooh, potential, electric potential. How is that defined? KQ over R. The electric potential is negative at some points on the line in which of the following ranges? To the left, between blah, blah, blah. Where is it going to be? It could be negative anywhere. They're all going to add up. Remember, electric potential is not a vector. It's a magnitude. It's just a value. It's just a number. So this one's going to cause K times 3Q over R anywhere around it. This one's going to cause K times 2Q over R anywhere around it. Both positive. If one of these was negative, that could be possible, but nope, that's not going to happen here. Both positive electric potentials. Answer is E. Okay, so 47, let's take a look. The graph above shows the electric potential V in a region of space as a function of position along the x-axis. Okay, so this is our potential as a function of distance. At which point would a charged particle experience the force of greatest magnitude? So now we need to recall, how do we relate how do we relate force and potential? Force and potential energy. And what you should recall is that work equals the integral of f dx, or conversely or inversely, force equals the derivative du dx. So when you're looking for force, and it's with a negative sign, but when you're looking for magnitude of force, where's it going to be? It's going to be where the slope is greatest. That's what it's going to be, where the slope is greatest. So we look at it here, a region B or region E, and it's a little hard for me to see because my eyes are not great, but obviously I think B here is where the slope is at its greatest. Obviously A and, D, what am I looking at? Sorry, excuse me. A at 0, C at 0, B and E kind of look the same. That's why I'm having trouble. It's D. D right here is the greatest slope, right? F equals du dx or dv dx in terms of electric field. And so D is where you're going to have the greatest force, because that's where the slope is greatest. Again, my eyes, your young eyes are much better than mine. So hopefully you saw that and didn't get fooled by B or E, but you realize that it depends on the slope. The magnitude is the slope of the V graph. The work that must be done by an external, the work that must be done by an external agent, again, ridiculous word, external agent to move a point charge of 2 millicoulombs from the origin to a point 3 meters away is 5 joules. What is the potential difference between these 2 points? How do we relate potential to work? Potential is change in internal energy, change in potential energy per unit charge. So just take your 5 joules of energy and divide it by Q. This 3 meters is completely irrelevant. It doesn't matter what the distance is. 5 joules is the work done. So let me put that down. Work equals the change in potential energy equals V times Q. And that's all it is. So if you want to know what the V is, take your work, divide by Q, and what is it going to be? It's 5 over 2. It's 5 over 2 millicoulombs, 2.5 times 7 right here. C. That's the answer. Okay. All right, 49. So I'm going through this kind of quickly. I'm trying to save space in this file, but I'm also, I'm trying to treat it as how you guys should approach it when you're doing your AP exam. You're not going to have time to do all of think about all of the calculations and do all the calculations. You need to just recognize right away the formula you need. Work equals V times Q, and plug it in and go. And that needs to come naturally. And I know we need practice with it, so that's what this is for. And we'll do a little bit more in the next couple weeks. 49. Okay, a rigid rectangular wire loop ABCD carrying current I1 lies in the plane of the page above a very long wire carrying current I2 as shown above. The net force on the loop is, well, let's see, current's going this way, current's going that way. Remember, if we do right-hand rule, all that stuff, we could do it. But here's the shortcut is that currents in the same direction that are parallel, they attract each other. And so these wires will try to come together. And up here, B to C, they're going to repel because they're further apart. Well, A to D is closer, so the net attraction is going to win out. And so we're going to have down, or rather toward the wire, and an attractive force here, A. And remember, if you do the right-hand rule, you can do the right-hand rule. You've got that I2 is causing a B field into the page at A to D. Use friends with benefits here. The force on that would be down because you've got current that way. That's your width. Your B is in, your benefit's into the page, so your thumb will be pointed down. That's an attraction, and that's the force that's going to win out over BC because it's further away. The magnetic field up there is less. Okay, so attracted toward the wire. 50. A uniform magnetic field B is parallel to the xy plane and in the positive y direction as shown above. A proton P initially moves with a velocity v in the xy plane at the angle theta to the magnetic field in the y-axis. The proton will subsequently follow what kind of path? Well, it's got a B field that's somewhat in the same direction as v, but partly there's a component of v that's perpendicular, right? And so that's the one that's going to matter. However, it's going to continue moving, and along with its y velocity is going to be constant. Its y component here is going to be constant. Why is that going to be constant? Because that component of velocity is parallel with b, and we know that magnetic force needs to only acts when the magnetic field is perpendicular to velocity. So the only component of velocity that's going to matter for the force is going to be this x component of velocity. That's going to create a magnetic force. That B field is going to create a magnetic force. Which way is that force going to be? That force is going to be, this is a bit of a tricky one, isn't it? Which way is it going to be? Friends with benefits says what? I've got V down and along the x direction. I've got B along the y-axis. So Z is going to be positive, for a positive charge, is going to be in the z direction. The force is going to be in the z direction. So what kind of path is it going to take? Well, if the force is in the z direction and the velocity were just in the x, it would go in a circle, right? But it's also got that y component. So it's going to have some kind of circular plus translational motion, and that will be a helix. That is going to make a helix. And so will it be a helical path with its axis parallel to the y-axis, or a helical path with its axis parallel to the z-axis? The circle is going to be going around the y-axis because the force is along the z-axis. So this is a tricky one. This is one to think about. The v is constant in the y, so it's not going to, and it is going to feel a force that's causing it to go in a circle. The circle is going to be a radius along the z-axis. It's going to be going along circularly, but continuing along the path given by Vy. So parallel, helical path with its axis parallel to the y-axis. Tricky question. That's where they get tricky. All right, so I've got a break here. I've got a class coming up. I'm going to come back to this in just a bit, and we'll look at 51. And 51 is interesting because that is one where we're going to use something called unit analysis. Even if we don't know how to solve it directly, we're going to be able to put it together.